Winter of 1915. Denver, Colorado. The American Institute of Mining Engineers would never fully grasp what they dismissed that frigid December morning. Dr. Heinrich Müller, the most respected excavation authority in Europe, stood before hundreds of American engineers with charts proving steam shovels had reached their absolute physical limit. 25 tons maximum lift capacity, no exceptions, no improvements possible. The laws of thermodynamics, he declared, made anything beyond this scientifically impossible. 800 miles east in Ohio, a young American engineer named William Corey was sketching cable configurations by lamplight, designing a machine that would shatter every European assumption about excavation power. Steel cables, electric motors, coordinated systems that European steam technology could never achieve. While Dr. Muller calculated theoretical limitations, American foundries were already building the revolutionary Model 120B, a machine designed to lift 50 tons, double what Europe's finest engineering minds insisted was the absolute ceiling. In the iron mines of Minnesota, the impossible was about to become routine, not through superior theory, not through complex mathematics, but through American innovation that would redefine the very meaning of excavation power. The applause that followed Dr. Heinrich Müller's presentation to the American Institute of Mining Engineers carried the weight of scientific certainty. Charts displaying steam pressure calculations covered the mahogany walls of Denver's Brown Palace Hotel ballroom, each graph reinforcing his central thesis with Germanic precision. Muller adjusted his wire-rimmed spectacles and surveyed the assembled American engineers with the confidence of a man who had spent 30 years perfecting excavation science at Europe's most prestigious mining academies. Gentlemen, Muller concluded, his accent lending gravity to each syllable, steam represents the absolute pinnacle of mechanical excavation. 25 tons maximum lift capacity while maintaining operational precision. This is not opinion. This is thermodynamic law. He gestured toward a detailed cross-section of the latest Ruston Bucyrus steam shovel, its massive boiler dominating the machine's profile. The relationship between steam pressure, cylinder displacement, and mechanical advantage permits no further advancement. We have reached the ceiling. The German engineer's reputation preceded him across American mining circles. His textbook on steam excavation methods had become the industry standard from Pennsylvania coal fields to Colorado's silver mines. When Mueller spoke about excavation limits, mining superintendents listened. His calculations had predicted equipment failures with uncanny accuracy, saving companies thousands of dollars in preventable breakdowns. But 800 miles northeast in South Milwaukee, Wisconsin, a different conversation was unfolding in the drafting rooms of Bucyrus Foundry. William Corey pushed aside his dinner plate and spread blueprints across the oil-stained oak table where the engineering team gathered each evening after the day shift ended. At 34, Corey possessed the restless energy of a man convinced that mechanical limits existed only until someone discovered how to transcend them. "Look at this steam shovel cross-section," Corey said, pointing to the massive boiler that consumed nearly half the machine's total weight. "We're hauling around tons of water and steel just to generate power. That's the real limitation, not the strength of materials or the laws of physics, but the inefficiency of carrying your power plant with you." His colleague Thomas Brennan, a master steam shovel operator whose calloused hands had controlled more excavation tonnage than any man in the Midwest, shook his head skeptically. "Bill, I've run every steam shovel model Bucyrus ever built. The 95B can move 200 tons per hour with surgical precision. You want to risk that proven performance on some electrical experiment?" Corey walked to the window overlooking the foundry floor, where the company's latest steam shovel, a 95-ton monster designated Model 95B, dominated the assembly bay. 8 men swarmed over its massive frame, fine-tuning the complex network of steam pipes, pressure gauges, and mechanical linkages that controlled its every movement. The machine represented the absolute state of excavation art, capable of lifting 20 tons while maintaining the precise control necessary for loading railroad cars without spillage. Yet Corey saw only limitations. The heavy boiler restricted lifting capacity. Steam pressure required constant attention from skilled operators who understood the delicate balance between power and safety. Most critically, steam systems responded slowly to control inputs. Fine adjustments took precious seconds that accumulated into significant productivity losses over full working days. Thomas, you're thinking like a steam engineer, Corey said, turning back to the blueprints. What if we eliminated the boiler entirely? What if power came from outside the machine through electrical cables like the overhead systems powering our factory cranes? The concept seemed almost heretical. Steam shovels had evolved steadily since their introduction in the 1870s, growing larger and more powerful with each generation. European manufacturers led this development, producing machines that American companies licensed and modified for local conditions. The fundamental architecture remained unchanged: boiler, steam cylinders, mechanical linkages. This was proven technology, refined through decades of field experience. But Corey had spent months studying the factory's overhead crane operations, watching how steel cables transmitted enormous forces through precision pulley systems with minimal energy loss. Electric motors provided instant, controllable power that could be coordinated with mechanical precision impossible in steam systems. The mathematics were compelling. Electric motors generated maximum torque at zero speed, exactly when excavation required maximum force. Company President Daniel Bucyrus entered the drafting room as Corey sketched cable routing diagrams for his revolutionary design concept. At 58, Bucyrus had built the foundry from a small Ohio operation into one of America's premier excavation equipment manufacturers by balancing engineering innovation with commercial pragmatism. His success depended on reading market trends correctly while avoiding costly development failures. Bill's been working on this electrical shovel concept for 6 months, Brennan explained. Claims it can lift 50 tons, double any steam shovel ever built. Bucyrus studied Corey's drawings with the practiced eye of a man who had evaluated hundreds of mechanical innovations. The design eliminated the massive boiler, replacing steam cylinders with electric motors connected through steel cable systems. Instead of pushing material away from the machine like traditional steam shovels, this design pulled material toward the operator using coordinated winch systems, controlled by precision electrical switches. The Ward-Leonard control system, Corey explained, pointing to electrical diagrams that showed multiple motor coordination. Instead of crude steam throttles, operators get fingertip control over crowd motor, hoist motor, and swing motor simultaneously. Perfect coordination, instant response, unlimited power as long as electrical supply holds. The technical elegance was undeniable, but Bucyrus understood the commercial risk. Steam shovels represented proven technology with established maintenance procedures and trained operators throughout American mining operations. This electrical concept would require completely new operator training, untested maintenance protocols, and electrical infrastructure that many mining sites lacked. Yet American industrial competition was intensifying. European manufacturers still dominated large excavation contracts, and their technical superiority in steam technology seemed insurmountable through conventional development. If Corey's electrical concept worked, Bucyrus Foundry could leapfrog decades of European engineering advancement with a single revolutionary design. How confident are you that 50-ton lift capacity is achievable? Bucyrus asked. Corey's response carried the conviction of a man who had performed the calculations dozens of times. Daniel, steam pressure physics creates absolute limits. Electrical systems don't have those constraints. With proper cable strength and motor coordination, 50 tons is conservative. We could probably reach 75 tons if the frame can handle the structural loads. The foundry president studied the ambitious young engineer whose confidence seemed to exceed prudent engineering judgment. Yet Corey had earned respect through hands-on problem solving that consistently improved production efficiency. His modifications to existing steam shovel designs had increased Bucyrus' market share significantly over the past 2 years. All right, Bill, Bucyrus decided. We'll commit to building your Model 120B, full electrical cable system, 50-ton design capacity, complete break from steam technology. But understand the stakes. If this fails, it could bankrupt the company. The first challenge emerged before Corey's team had even completed the foundational framework for the Model 120B. Traditional steam shovel design pushed material away from the operator using mechanical arms powered by steam cylinders. This approach worked because steam pressure provided steady, predictable force that operators could manage through throttle controls and mechanical linkages. But electrical systems demanded entirely different engineering principles. Corey stood before a blackboard covered with force diagrams, explaining the fundamental reversal his design required. Gentlemen, we're not adapting steam shovel architecture to electrical power. We're reinventing excavation from first principles. He drew arrows showing material flow toward the machine rather than away from it. The electrical system pulls material to the operator using steel cables and electric winches, like a massive fishing reel with industrial precision. The engineering implications were staggering. Instead of mechanical arms pushing against resistance, the new system required coordinated cable management that could handle enormous loads while maintaining smooth operation. 3 separate motor systems had to work in perfect harmony: the crowd motor controlling bucket positioning, the hoist motor managing vertical lift, and the swing motor handling rotation. Any miscalculation in timing or force coordination could result in catastrophic cable failure. Thomas Brennan, whose steam shovel expertise made him invaluable despite his skepticism, identified the critical control challenge. Bill, in a steam system, I've got direct mechanical feedback through the throttle and gear systems. I can feel the load, sense the resistance, adjust pressure incrementally. How does an operator coordinate 3 electrical motors simultaneously without mechanical feedback? Corey's answer lay in the Ward-Leonard control system, an electrical innovation that promised to revolutionize industrial motor control. Instead of crude on-off switches, the Ward-Leonard system provided infinitely variable speed control through generator motor combinations. Operators could coordinate multiple functions using fingertip pressure on electrical levers, achieving precision impossible with mechanical steam controls. Thomas, imagine controlling bucket crowd, hoist speed, and swing rotation with the same delicacy you'd use to thread a needle, Corey explained, demonstrating on a scale model. The electrical response is instantaneous. No lag time for steam pressure buildup. No mechanical play in gear systems. Pure electrical control translating operator intentions directly into machine movement. The materials engineering challenge proved equally complex. Steel cable technology, while established in crane applications, had never been tested under the cyclical loading conditions that excavation demanded. Each cable had to withstand 50-ton loads repeatedly throughout 12-hour working shifts while remaining flexible enough for smooth operation over pulley systems. The cables would stretch and contract under load, requiring constant tension adjustment to maintain proper operation. Bucyrus Foundry's metallurgy department, led by Chief Engineer Robert Walsh, developed new cable weaving techniques specifically for excavation applications. Traditional crane cables used parallel wire construction that provided maximum strength but limited flexibility. Walsh's team created helical wire patterns that distributed stress more evenly while maintaining the flexibility necessary for continuous cycling over pulleys. We're testing braking strengths that would hold a fully loaded locomotive suspended in midair, Walsh reported during weekly engineering meetings. But braking strength alone isn't sufficient. These cables must maintain precise tension under varying loads while operating smoothly over pulleys spinning at different speeds. The cable tensioning system required mechanical innovation that approached watchmaking precision scaled up to industrial proportions. Corey designed automatic tensioning mechanisms using spring-loaded pulleys that maintained constant cable tension regardless of load variations. The system had to compensate for cable stretch under load while preventing slack that could cause dangerous cable whipping or pulley damage. By spring of 1918, the first Model 120B began taking shape on Bucyrus Foundry's assembly floor. The machine's silhouette looked unlike any excavation equipment ever constructed. Where steam shovels carried massive boilers, the electrical model featured a compact operator compartment surrounded by precision cable management systems. The overall weight was significantly reduced, 60 tons compared to 95 tons for equivalent steam models. Yet the design specifications promised double the lifting capacity. The electrical installation required expertise that few American factories possessed. Corey contracted with General Electric to provide motor systems and control equipment, while Western Electric supplied the complex switching mechanisms that would coordinate multiple motor functions. The electrical cabinet alone contained more precision components than most complete steam shovels. Initial testing began in the foundry's equipment yard, using carefully measured loads suspended from the machine's bucket. The results exceeded even Corey's optimistic projections. The electrical system lifted 4 cubic yard buckets, twice the capacity of the largest steam shovels, with smoothness that amazed veteran operators. The Ward-Leonard control system provided precision that allowed operators to position massive loads within inches of target locations. Thomas Brennan, assigned to master the new electrical controls despite his steam shovel background, discovered capabilities that transformed his understanding of excavation possibilities. "Bill, this machine responds to my intentions, not just my actions," he reported after his first week of testing. "In a steam shovel, I fight the machine to achieve precision. Here, the machine amplifies my precision." The coordination between 3 motor systems created operational possibilities impossible with steam technology. Operators could simultaneously crowd the bucket into material while hoisting previous loads and swinging toward dumping positions. The electrical system's instant response eliminated the sequential operations that steam systems required, potentially increasing productivity far beyond the 50% improvement that doubled lifting capacity suggested. Word of the successful tests spread through American mining circles with the speed that revolutionary technology always generates. Mine superintendents who had dismissed electrical excavation as impractical began requesting demonstrations. Equipment dealers who specialized in steam shovels started inquiring about electrical model availability. European manufacturers, initially dismissive of American electrical experiments, began monitoring Bucyrus developments with growing concern. But the Model 120B remained unproven in actual mining conditions. Foundry testing used controlled loads under ideal weather conditions with skilled technicians available for immediate adjustments. Real mining operations demanded reliable performance in harsh environments, with operators whose electrical experience might be limited. The machine's revolutionary capabilities meant nothing if it couldn't maintain productivity under the demanding conditions that mining operations required. The M.A. Hanna Company, which operated extensive iron mining operations near Hibbing, Minnesota, agreed to provide the ultimate test of electrical excavation technology. Mine Superintendent John Harrison had built his reputation on extracting maximum tonnage from proven equipment. His willingness to risk production schedules on unproven technology reflected both the potential rewards and the confidence that American engineering innovation might finally challenge European excavation dominance. "Gentlemen," Harrison told Corey's team as the Model 120B was transported to Minnesota, "I've got production quotas that keep 800 men employed. This machine better work better than 3 steam shovels, or you're paying for lost tonnage." The Model 120B arrived at the M.A. Hanna Company's Hull Rust Mahoning mine on a frigid October morning in 1918, transported by 3 railroad flat cars through the iron ranges of northern Minnesota. Mine Superintendent John Harrison watched the unloading process with the skeptical eye of a man whose career depended on extracting maximum tonnage from equipment that worked reliably in conditions that destroyed lesser machines. The Mesabi Range's iron ore deposits lay exposed in open pits that stretched for miles, requiring excavation equipment capable of loading 50-ton railroad cars with precision that prevented spillage and maintained production schedules. Harrison's operation employed the most advanced steam shovels available, 3 Bucyrus Model 95B machines that had established productivity records throughout Minnesota's iron mining district. Each steam shovel required an 8-man crew working in coordinated shifts to maintain the constant fuel supply, water levels, and mechanical adjustments that sustained 20-ton lifting capacity throughout 12-hour operations. The machines loaded approximately 100 railroad cars daily, moving 8,000 tons of iron ore that supplied steel mills from Pittsburgh to Gary, Indiana. "Bill, I've built my reputation on equipment that works when the temperature drops to 30 below and the wind cuts through this pit like a knife," Harrison told Corey as they surveyed the massive excavation operation. Your electrical machine looks impressive in a foundry, but this Minnesota winter will test every component you've designed. The first operational tests began immediately, with Thomas Brennan operating the Model 120B alongside Harrison's best steam shovel crews. The electrical machine's performance exceeded even Corey's optimistic projections from the foundry trials. The coordinated motor systems allowed Brennan to load railroad cars 40% faster than steam shovels, positioning 4 cubic yard buckets with precision that eliminated spillage and reduced loading time per car from 12 minutes to 7 minutes. The operational advantages became apparent within hours. While steam shovels required sequential operations, crowd the bucket, lift the load, swing to position, dump the material, the electrical system enabled simultaneous coordination of all functions. Brennan could crowd the bucket into ore deposits while simultaneously swinging toward the next railroad car and adjusting hoist speed for optimal dumping angle. The Ward-Leonard control system responded to fingertip pressure with accuracy that allowed him to place 50-ton loads within inches of target positions inside railroad cars. Most significantly, the electrical machine required only Brennan and one assistant to achieve productivity that demanded 8-man crews on steam shovels. The elimination of coal handling, water management, and constant mechanical adjustments freed operators to focus entirely on excavation technique. Harrison's production records showed immediate improvement. The Model 120B loaded 170 railroad cars during its first full operational day, representing 12,000 tons of iron ore moved by 2 operators. Word of the Minnesota results spread through American mining circles with the rapid communication that revolutionary technology always generates. Mining superintendents from Pennsylvania, coal fields to Colorado copper operations requested detailed performance reports. Equipment dealers who had built their businesses on steam shovel sales began inquiring about electrical model availability and delivery schedules. The American Institute of Mining Engineers scheduled emergency sessions to evaluate electrical excavation technology. But the news traveled beyond American industrial circles. European engineering publications began reporting the Minnesota tests with the mixture of skepticism and concern that established technical authorities displayed when confronted with innovations that challenged fundamental assumptions. Dr. Heinrich Müller, whose Denver presentation had declared steam excavation limits absolute, published a detailed analysis in Engineering News that questioned the American claims. The reported performance figures from Minnesota operations appear to violate established principles of mechanical advantage and power transmission, Müller wrote. European experience with electrical excavation experiments has consistently demonstrated that motor coordination problems and cable failure rates make such systems unsuitable for reliable mining operations. American optimism should not substitute for rigorous engineering analysis. Muller's critique reflected broader European confidence in steam technology superiority. German and British manufacturers had perfected steam excavation through decades of systematic development, creating machines that represented the accumulated wisdom of European mechanical engineering. The suggestion that American electrical experiments could suddenly surpass this established technology seemed to challenge not only specific equipment designs, but the fundamental approach to industrial development. The European response intensified when detailed specifications of the Model 120B reached technical publications across Germany, Britain, and France. European engineers analyzed the cable systems, motor coordination mechanisms, and control technologies with the methodical thoroughness that characterized continental technical evaluation. Their conclusions consistently questioned whether the American claims could be sustained under rigorous operational conditions. The Americans report cable systems handling 50-ton loads with reliability that exceeds our most advanced steam mechanisms, observed Professor Ernst Zimmermann of the Berlin Technical Institute. Such claims require verification under European testing standards before they can be accepted as legitimate engineering achievements. The skepticism reflected deeper cultural differences in engineering philosophy. European technical education emphasized theoretical foundations, mathematical analysis, and systematic testing protocols that validated innovations before implementation. American industrial development prioritized practical results, accepting higher risk levels in pursuit of breakthrough performance improvements. These philosophical differences had created productive tension in previous technological competitions, but electrical excavation seemed to represent a more fundamental challenge to European technical supremacy. Harrison monitored the European reaction with the satisfaction of a man whose practical judgment had been vindicated by results that theoretical analysis had declared impossible. The Model 120B continued exceeding performance expectations throughout its Minnesota testing period, maintaining production levels that consistently surpassed steam shovel capabilities while demonstrating reliability that quieted initial concerns about electrical system complexity. These European engineers can publish all the theoretical objections they want, Harrison told Corey during the machine's third week of operation. My production records show 12,000 tons daily from 2 operators using your electrical system compared to 8,000 tons from 24 operators using their steam shovels. Mathematics can't argue with tonnage moved. The Minnesota success established electrical excavation as legitimate technology worthy of serious industrial consideration. Mining companies throughout America began evaluating electrical systems for their operations, recognizing that labor cost reductions alone justified the transition from steam technology. Equipment manufacturers started developing their own electrical models, attempting to capture market share in what appeared to be a fundamental shift in excavation technology. But the most significant impact occurred in European engineering circles, where the American success forced reconsideration of established technical assumptions. If electrical excavation could achieve the performance levels reported from Minnesota, European manufacturers faced the prospect of technological obsolescence in markets they had dominated for decades. The American challenge to steam excavation supremacy had evolved from theoretical possibility to demonstrated reality that demanded response. The catastrophe struck during the third week of November, when Minnesota temperatures plunged to 18 degrees below zero, and the Model 120B was scheduled for its most critical demonstration. Representatives from 6 major mining companies had traveled to Hibbing specifically to evaluate electrical excavation technology for their operations. The group included procurement officials from Bethlehem Steel, Republic Steel, and the Consolidation Coal Company, industrial giants whose equipment decisions could determine whether electrical shovels achieved widespread adoption or remained experimental curiosities. Thomas Brennan began the demonstration, loading railroad cars with the smooth precision that had characterized the machine's performance throughout its Minnesota trials. The electrical systems responded flawlessly to his control inputs, coordinating crowd motor, hoist motor, and swing motor with mechanical harmony that impressed even skeptical observers. The 4 cubic yard bucket moved through loading cycles with efficiency that clearly surpassed steam shovel capabilities, positioning massive iron ore loads with accuracy that eliminated spillage and maximized car capacity utilization. But as Brennan attempted to lift a particularly heavy load of high-grade iron ore, approximately 52 tons total weight, the primary hoist cable suddenly snapped with a metallic crack that echoed across the mining pit like rifle fire. The massive bucket, suspended 40 feet above the railroad car, crashed downward with devastating force. The impact destroyed the bucket assembly, bent the boom's structural framework, and sent shock waves through the machine's superstructure that cracked welds and loosened critical mounting bolts. The failure cascaded through interconnected systems with the speed that complex mechanical disasters always generate. The broken hoist cable whipped across the operator compartment, forcing Brennan to dive for cover as steel strands slashed through the air with lethal velocity. Secondary cables, suddenly carrying loads they were never designed to handle, began failing in sequence. The crowd motor, deprived of coordinated hoist support, stalled under excessive load and began overheating. Within minutes, the revolutionary Model 120B sat disabled in the Minnesota pit, its twisted cable systems and damaged framework providing stark testimony to electrical excavation's apparent limitations. John Harrison immediately ordered the mining pit cleared, while Corey's engineering team began investigating the failure. The examination revealed problems that struck at the heart of electrical excavation technology. Cold weather had made the steel cables brittle, reducing their flexibility and making them susceptible to sudden fracture under loads they had handled successfully during warmer conditions. The cable tensioning system, designed to compensate for normal thermal expansion and contraction, could not adjust rapidly enough for the extreme temperature changes that Minnesota winters imposed. More critically, the investigation revealed fundamental design flaws in the cable coordination system. Steam shovels used mechanical linkages that automatically adjusted to varying load conditions through purely mechanical responses. The electrical system required precise coordination between multiple motors but lacked the mechanical feedback systems that would have warned operators when individual components approached failure limits. Brennan had no indication that the hoist cable was approaching its breaking point until catastrophic failure occurred. "Bill, this isn't just a cable problem," Harrison told Corey as they examined the damaged machine. "Your electrical system has no safety margins built into the coordination mechanisms. When one component fails, everything fails. Steam shovels break down gradually, you get warning signs, declining performance, opportunities to prevent catastrophic damage. This electrical system fails completely and instantly." The timing of the failure could not have been worse for electrical excavation's commercial prospects. The demonstration had been specifically arranged to showcase the technology's superiority over steam shovels for potential industrial customers, whose combined purchasing power represented millions of dollars in potential orders. Instead, they witnessed a spectacular failure that reinforced every concern about electrical system reliability that conservative mining engineers had expressed. Word of the Minnesota disaster spread through American mining circles with the rapid communication that technological failures always generate. Mining superintendents who had been considering electrical excavation postponed their evaluations pending investigation of the failure causes. Equipment dealers canceled preliminary orders for electrical shovels, returning to proven steam technology that might be less efficient but demonstrated consistent reliability. The American Institute of Mining Engineers scheduled emergency sessions to reassess electrical excavation's commercial viability. The European engineering response was swift and decisive. Dr. Heinrich Müller published a detailed analysis of the Minnesota failure in Engineering News that positioned the disaster as vindication of European skepticism about American electrical experiments. The catastrophic failure of the Bucyrus electrical excavation system demonstrates precisely the coordination problems that European engineering analysis predicted, Muller wrote. Complex electrical systems cannot match the inherent reliability of proven steam technology under demanding operational conditions. European manufacturers seized the opportunity to reinforce their technological superiority in excavation equipment markets. German and British companies began aggressive marketing campaigns that emphasized steam shovel reliability, highlighting decades of successful operation in harsh conditions worldwide. The message was clear. American electrical innovation might promise impressive performance, but European steam technology delivered dependable results that mining operations could trust with their production schedules. The commercial impact on Bucyrus Foundry was immediate and severe. Orders for new electrical shovels stopped entirely as potential customers returned to established steam technology. Mining companies that had been negotiating purchase contracts for electrical equipment canceled their agreements, citing reliability concerns that the Minnesota failure had confirmed. Company president Daniel Bucyrus faced the possibility that his decision to bet the company's future on electrical excavation might result in financial catastrophe. "Bill, we've got 47 orders canceled in the past 2 weeks," Bucyrus reported during an emergency board meeting. "Our dealers are telling customers to wait for proven technology rather than risk their operations on experimental equipment. The Minnesota failure has destroyed 5 years of market development in 5 minutes." Industry publications began running articles questioning whether American innovation had outpaced engineering reality. The consensus among technical experts suggested that electrical excavation represented premature technology, potentially viable in the future, but insufficiently developed for reliable industrial application. Steam shovels might have performance limitations, but they provided predictable operation that mining companies required for profitable operations. Thomas Brennan, whose operational expertise had made him invaluable during the electrical system's development, found himself questioning fundamental assumptions about technological progress. "Bill, I've spent 6 months learning to operate electrical systems that promise to make me more productive than any steam shovel operator in America, he told Corey. Now I'm wondering whether we've been chasing impossible dreams while ignoring the practical wisdom that steam technology represents. The failure forced Corey to confront the possibility that his revolutionary vision might have been technically premature. The engineering challenges that electrical excavation presented, cable coordination, motor synchronization, thermal compensation, might require years of additional development before achieving the reliability that commercial operations demanded. European critics seemed vindicated in their assertion that established steam technology represented the practical limit of excavation capabilities. But Corey refused to abandon the electrical concept despite mounting pressure to return to proven steam shovel development. The Minnesota failure had revealed specific engineering problems, not fundamental flaws in electrical excavation principles. Cold weather cable brittleness could be solved through improved steel metallurgy. Cable tensioning systems could be redesigned to handle extreme temperature variations. Motor coordination could incorporate safety systems that prevented cascading failures. Corey's response to the Minnesota disaster defied every conventional engineering wisdom about managing technological failure. While competitors abandoned electrical excavation and returned to steam shovel development, he convinced Daniel Bucyrus to invest the company's remaining resources in solving the specific problems that had caused the catastrophic breakdown. The solution required advances in 3 critical areas: steel cable, metallurgy, thermal compensation systems, and coordinated motor control with built-in safety mechanisms. The cable problem demanded collaboration with American Steel and Wire Company, whose metallurgists had been developing new alloy compositions for bridge construction and elevator systems. Traditional excavation cables used high-carbon steel that provided maximum tensile strength but became brittle in cold temperatures. Corey's team worked with steel chemists to develop new alloy formulations that maintained flexibility down to 40 degrees below zero while retaining the 50-ton load capacity that electrical excavation required. The breakthrough came through adding carefully controlled amounts of nickel and chromium to the steel composition, creating cables that retained flexibility across temperature ranges from subtropical mining operations in Arizona to Arctic conditions in Minnesota iron ranges. Testing protocols developed at Bucyrus proved the new cables could withstand repeated loading cycles that simulated 5 years of continuous mining operation without degradation in performance characteristics. Simultaneously, Corey redesigned the cable tensioning system to handle extreme thermal expansion and contraction through mechanical compensation that operated independently of electrical controls. The new system used spring-loaded pulleys with adjustment ranges that automatically maintained proper cable tension as temperatures varied throughout operational cycles. Most importantly, the mechanical tensioning system provided visual indicators that warned operators when cables approached stress limits, eliminating the sudden failures that had characterized the Minnesota disaster. The motor coordination challenge required developing entirely new control systems that incorporated safety mechanisms without compromising operational efficiency. Working with General Electric's research division, Corey's team created electrical monitoring circuits that continuously measured load conditions on each motor system. When any component approached failure limits, the control system automatically reduced power to prevent catastrophic overload while maintaining coordinated operation of remaining systems. The redesigned Model 120B incorporated these improvements into a machine that retained all the performance advantages of electrical excavation while addressing every failure mode that Minnesota testing had revealed. The new cables handled 50-ton loads reliably across extreme temperature ranges. The improved tensioning system prevented sudden cable failures through continuous monitoring and automatic adjustment. The enhanced motor controls provided built-in safety margins that prevented cascading system failures. By spring of 1920, Bucyrus had completed construction of the perfected electrical excavation system and arranged the definitive demonstration that would determine whether American electrical technology could challenge European steam shovel dominance. The Ohio Coal Mining Company agreed to provide testing facilities at their massive strip mining operation near Zanesville, where direct comparison between electrical and steam technology could proceed under identical conditions. The demonstration was structured as a formal competition between the redesigned Model 120B, and the finest European steam shovels available in American markets. The German-built Menck and Hambrock Model 45 represented the pinnacle of European excavation engineering, incorporating decades of systematic development that had produced steam shovels capable of 25-ton lifts with remarkable reliability. British Ruston Bucyrus steam shovels provided additional comparison, ensuring that electrical technology faced the strongest possible steam shovel competition. John Harrison, whose Minnesota experience had made him the most knowledgeable American authority on electrical excavation capabilities, supervised the comparative testing protocols. The evaluation criteria included productivity measurements, operational reliability, maintenance requirements, and operator skill demands that would determine whether electrical systems offered genuine advantages over established steam technology. The results spoke with numerical precision that eliminated subjective evaluation. The Model 120B, operated by Thomas Brennan, with assistance from one helper, loaded 500 tons of coal per hour compared to 200 tons per hour from steam shovels requiring 8-man crews. The electrical system demonstrated 50-ton maximum lifting capacity compared to 25 tons for the largest steam shovels. Most significantly, the electrical machine maintained consistent performance throughout 12-hour operational shifts without the declining efficiency that characterized steam systems as coal supplies diminished and boiler pressures fluctuated. The operational precision differences were equally dramatic. Steam shovels required sequential operations that limited productivity. Operators had to complete bucket positioning before initiating lifting operations, then wait for pressure buildup before beginning swing movements toward dumping positions. The electrical system enabled simultaneous coordination of all functions, allowing operators to crowd buckets into material while simultaneously lifting previous loads and positioning for optimal dumping angles. Labor efficiency advantages exceeded even Corey's optimistic projections. The electrical system's 2-man crew achieved productivity that required 24 operators across 3 steam shovel teams. The elimination of coal handling, water management, and constant mechanical adjustments allowed operators to focus entirely on excavation technique. Maintenance requirements were dramatically reduced. Electrical systems required periodic cable inspection and motor lubrication compared to steam shovels' complex boiler, maintenance, mechanical linkage adjustments, and continuous fuel supply logistics. The technical explanation for electrical superiority was rooted in fundamental physics that European engineers had overlooked in their commitment to steam technology refinement. Steam pressure created inherent limitations through thermodynamic laws. Energy conversion from coal combustion to mechanical work involved significant losses through heat dissipation and mechanical friction. Electrical motors converted energy with 95% efficiency while providing maximum torque at 0 speed, exactly when excavation operations required maximum force. Steel cables transmitted this electrical power with minimal energy loss, creating direct mechanical advantage that steam systems could not match. The coordination of multiple electrical motors through precision controls enabled simultaneous operations that steam systems' sequential limitations prevented. Most critically, electrical power could be supplied continuously from external sources, eliminating the weight penalties and operational constraints that steam shovels' onboard power generation imposed. European engineering publications initially dismissed the Ohio demonstration results as American promotional exaggeration, but independent verification by British mining engineers confirmed the performance claims. Dr. Heinrich Müller, whose theoretical analysis had declared electrical excavation impossible, traveled to Ohio personally to observe the Model 120B in operation. His subsequent report acknowledged that American electrical excavation had achieved capabilities that European steam technology could not match. The American electrical excavation system demonstrates performance characteristics that our theoretical analysis failed to predict, Mueller wrote in his revised assessment. While steam technology represents the culmination of European mechanical engineering excellence, electrical systems appear to transcend the fundamental limitations that constrain steam power applications. The admission represented more than individual recognition of technological superiority. It marked the end of European dominance in excavation equipment markets that had lasted for over 50 years. American electrical innovation had not merely improved upon existing technology, but had created entirely new capabilities that redefined excavation possibilities. Within 18 months of the Ohio demonstration, European manufacturers began licensing American electrical technology rather than competing against capabilities they could not duplicate through steam system refinements. The completed Panama Canal expansion project provided the ultimate vindication of American electrical excavation superiority. Dozens of Model 120B machines moved millions of cubic yards of earth with efficiency that made the canal expansion economically viable for the first time. European observers, witnessing American excavation, capabilities that their own technology could never achieve, acknowledged that the fundamental transformation of excavation technology had shifted permanently from European steam systems to American electrical innovation.